here is a sort of a more involved problem, something which I think you ought to know, because if you are designing something, you need to be able to analyze loading condition and figure out which is the most critical point for the maximum stress. And then, once you have that, you can then see which part will fail first. And if you know that, then you can do the inverse problem, which is you can then start designing the components or laying them on the shaft so that the stresses are lower. Okay, the inverse problem is often harder. It requires multiple iterations. You go back and forth, and you probably don't want to do it by hand. You want to write a program which will do it for you. Okay, so let's see how to solve this one. Okay, for the shaft shown below, the mating gears not shown. Drive the gears B and D. So these are the gears B and D. So there's a gear which runs them that's not shown. Through force in the vertical direction. So those forces are 2000 and 6000 as shown. Assume SUT, SY, SC, those three numbers. Compute the factor of safety assuming static yielding using distortion energy, and factor of safety assuming fatigue failure and DESME elliptic curve. Okay, so I think the best way to deal with such a problem is to ask yourself, what is the formula for factor of safety based on static yielding? And so I'll try to write those formulas down first, A and B, and then ask myself what I need to solve to get the required values in those expressions, and that will help me to then continue solving this problem. So you asked PEA semi-elliptic and distortion energy, and that's equations, I think the 4 and 5, just what I wrote down some time back. This one. So factor of safety, so I need to get this one. Okay, and then the other one is the yield, this one. And a better way to copy these things. Copy. I think I'm doing a mistake in pasting it. Whatever. Okay, so this is the first cycle yielding. So if I'm not mistaken, we need A and B. So this is solution to B, this is solution to A. This was also formula 4, formula 5 when you refer the notes. Okay, so let's see what we need and what do we have. We need the following things. We need D, we need SY. Now let me just go one by one per this order. KF, KFS, TA, T, M, MA, MM, SY, SE, SUT. A lot of things. So I'm just going to put down whatever I know. SUT is 100 kpsi. SE. So here is your given SE already. You don't have to adjust it. This is the for the specimen given. It's not for the lab specimen, so you don't have to correct it. SY is 80. K. So D will depend on which part is going to be critical. KF, KFS is something which only comes into a picture if there's a stress concentration, right? And then we have TA, TM, MA, MA. So these things for this we need to. So the previous problem, like this one, here we were pretty much given M and T, right? The torque was uniform, M was uniform, and so we didn't have any problem figuring out MA, MM, and so on. But in this problem, it's less obvious because the loading is more general, and then the stress or the moment and torque at different points is going to vary. So the only hope we have here is to figure out the shear force and the bending moment diagram. So we need, for M, we need bending moment diagram. And for torque, there is an equivalent diagram called the torque diagram, which is just plotting the torque as a function of a distance along the shaft. And once we have that, we should have those values. Okay, so these factors will depend on only if there is stress concentration. Okay, so in other words, if we figure out that the stress is maximum over here, right, that point doesn't have any stress concentration because the geometry doesn't change. However, if that critical point is going to be here, then clearly there is a stress concentration. So we will have KFS not equal to 1. So it's 1, KFS is 1, KF and KFS is 1 over here, but it's not equal to 1. We need to look at the appropriate table to figure out what to do. And then the D depends on critical location. That's the critical location for stress. Okay, so it looks like our best hope is to first figure these things out. And that will inform these 3 things. Okay, so sort of we go back to some of the earlier things we did in this course, which is shear force and shear force diagram, because that will help us to draw the bending moment diagram and then the torque diagram. So let's do that. Okay, so what I'm going to do is take a shortcut here, have a view of this. Blow it up a little bit. Okay, I'm going to try to attempt to draw the shear force diagram and bending moment diagram. But before I do that, I need to draw a free body diagram in order to figure out the reaction forces. Remember that the axis represents bearings. So let me just, you want to get, since I made a copy of this, let me make another copy of this. I'll need it for the next diagram. Copy. Okay, so the way you draw free body diagrams is get rid of the supports. In this case, this will go away and will be replaced by a force. Now I'm going to assume that this force is right here. So reaction at, or vertical reaction at A. And I'm assuming that the other vertical reaction, let me just change the color. Obvious. E A and VE. Okay, so you probably are experts at this. I just put down the values. I will not go through the details of computing the reaction forces. So what you need to do is summation of the forces in the y direction is 0. And then you need to do summation of moments about any point. Let's say A is 0. So that is two equations and two unknowns. And the unknowns are VA and VE. So you can solve for VA and VE. And if you do that, you get VA equals 3,200. And the load should be an LB force. Like this should be LBF. Okay, so that's, I skipped that step, but convince yourself that those are the reaction forces. Okay, so once we get that, let's now get to the shear force bending moment diagrams. Okay, so now what I'll do here is replace F, this is F. So again, get rid of this. Replace that with the force of, this case, 200, right? 200. And then get rid of the bearing. Yeah.
Professor, I have a good question. If this 1.5 inches is in the middle of the 600, like, can you explain me that, like, 1.5 inches, how, from where to where it is?
Sure. Sure. One sec. Give me a sec. I will explain. 3,800. So the dimensions are from here to here is 1.5. And then here to here is 1. From there to there is 1. And from here to this edge is 1. So this 1.5. Sorry, this should be in inches. Is that clear?
Yeah, makes sense. Thank you, Professor.
Yeah. Okay, so I'm going to draw the shear force diagram because it's not needed in this problem, because you see that there's no shear, the stress due to shear force, but we need it for the bending moment diagram. It will make our life easy, but not required if you can figure out the bending moment diagram without drawing the shear force diagram. For that, in order to figure out the bending moment without drawing the shear force diagram, you'll have to just cut the beam. Think of this as a beam, cut it at different points and write the bending equation, and you get the values. Okay, so
very similar to this
yes, yeah,
so
yeah.
like
That's like a beam, right? Right. Okay, so on the right, it starts at goes to 200. Okay, it'll remain constant. Then it shoots up by 2,000. So we need to add 2,000 to 200. And they'll keep going all the way to here. Now we'll have to subtract 6,000 from 2,200. That would be 3,800 with the negative sign. Or we're going to go all the way down. Okay, and then here we see it's 3,800, so it will go back to 0. So V as a function of X. We'll quickly run out of space. Think it a little bit. Okay, so let's do the bending moment diagram. So this is a trick which works very well for bending moment diagram is you could compute the area under the shear force diagram. So we have, here it's important to show this distance. This is 1 inch, this is 2.5 inches, and this is 1.5. Okay, so okay, so we need to do 1 times 200, which is 200. This is going to be 2200 times 2.5, which comes out to be 5 by 2, I think 5,500. And then here we have 3,800 times 1.5 with a negative sign. So that's 19 by 2. Just complete it. 5700. Okay, so with that, I think we can draw the diagram for bending moment. In fact, it's all be positive, so I just need to go a little down. Okay, so starts off with 0, because clearly at this left-hand side, there's no moment. And then we need to travel 200 up till the point so we need to go 200 because the area under the curve is 200. From here, we need to go 5,500, which needs to be added to this. So 5,700 way up. Okay, and then we need to go back down by 5,700 because the area under the curve is 5,700. So it's close to 0. Okay, and then one point of interest, I think, is this point where there is a sudden change of geometry. So I'm just going to put the value. So the way you can find this value is you can split this area into 2 parts. The area on the right, so the sum is 5,500, but the area on the right is, so 1 times, so area on the left is 1 times, so 2,200, because 1 times 2,200, and the right one is going to be 3,300. Or you can just do 2,000 times, 2,200 times this distance for the left one, and 2,200 times 1.5, the right one. Okay, which means that this point is going to be, you have to add 2,200 to 200, so 2,400. Because I just take this 2,200, add it to 200, and that's the point. Okay, and I'm just doing that because I think that that point is an important point because the geometry changes, so there'll be a stress concentration. I'm doing this to find a critical location. Okay, the final one is the torque diagram. Okay, so we've so far not really done too much about torque diagrams, but they pretty much tell the torques as a function of distance. The only two places where there are torques, if you can see in this figure, are there's a torque here due to this force, and there's a torque on this gear due to the 6,000 force. Now, you're also given the radius, it's 9" for RB and 3" for RD. So the torque at B is going to be 2000, it should be LBS. Also 2000 times 9, which is 1800 LBF in, and then PD is going to be 6,000 times 3, because the radius is 3. So 1800 LBF in. And you can notice that one of them, if the 2001 is counterclockwise, the 6001 is going to be clockwise. So the net torque on this shaft is going to be 0. Okay. So we have, so we just need this information in order to draw the torque diagram. The torque is 0 on the left side, 0 on the right side, but going from here to here, the torque increases suddenly to 1800, and then it's 1800 all the way till this point where it goes back to 0 because the torque is now the counterclockwise direction, and then it's 0 again there. So the torque diagram will be something like this. Yeah, I need. Okay, so it will start off right at gear B and then end at gear D. Question? 18,000, did I do a mistake there? Yeah, 18,000, that's right. Right, 18,000. So that is 18,000. LPF. Okay, so okay, what was the purpose of doing all this? Well, I said the purpose is to figure out these things, TA, TM, MA, MM. And in order to figure that out, we need to find the point which is going to have the highest stress. Okay, highest stress comes because the TA, TM, MA, MM is the highest. Now, if you go and look at this plot, you can see that the torques are high here. So it seems that this part, from this point to this point, all these points are critical for torque. Let's look at the moments now. So it's going to be the moments which are going to be the deciding factor because the torques are the same. So we have the torque, the moment increases, it goes to maximum here, and it is some intermediate value here. Now what you could do is, in this case, I think there are 2 points which are critical. One is this point where you can see that there is a moment and a torque. Both of moment is maximum, torque is maximum, and this point is critical now, even though the moment is not that high. It's because of stress concentration. Because of the stress concentration factor, the moment here is going to be a lot higher than what it is. It's going to be Kf times 2,400, and the torque will be, yeah.
What point you're talking about? Because we cannot see.
Oh, you cannot see. Yeah. So this point is going to have, let's call this B, and D. Okay, point B is going to have a much higher stress because of the stress concentration. It's just my bad. Let's call that C. So I have it C there. C. So point C is going to have much higher stresses because of stress concentration. So the actual torque moment at C is going to be Kf times the actual moment, 2,400, and the torque at C is going to be Kf times 18,000, just because that's the point of stress concentration. So between the C and D, the point which is more critical is actually C and not D. And I did this calculation outside the class, so I know it, but you wouldn't know it. You would want to do the calculation for C and do it for D. That is the calculation I'm going to show, and then decide for yourself which point is critical. Okay, so I'm sort of taking a shortcut here because I did some work outside the class. So I'm going to write this, and then Yao will take over. Point C and point D are possibly critical locations. However, because C has stress concentration, due to change in geometry, the actual moment and torque will be amplified by a factor Kf for moment and Kfs respectively. Okay, so we will use point C to compute the factor of safety. Okay, so I'm going to stop and let Yao take over, and whatever you talk with him is confidential. I'm not listening. I've not signed on Zoom, and you can use my Zoom, or you can use.
So you can.
Oh, sure, I can leave. I'm not signed in. It's not like I have access to it, but I can log off if that's. They cannot see the screen.
Stop recording.
Stop sharing and stop recording. Okay, so we have to compute TA, TM, MA, MM, and we'll do it at, this is all at C. Okay, and then when you see the formulas, so when we have this MA, note that it's going to be multiplied with KF later. So this is assuming that there's no change in geometry when we're computing, when we're writing the value for MA and T and so on. Okay, so what are those values? So what's happening here is that there is the mating gears are transmitting torques, right? So since the torques being transmitted, in this case, we're going to assume that the mean torque is whatever we get from that figure. So that's going to be the mean torque, 2,400. Sorry, 18,000. Sorry, and then the now if that's the mean torque, okay, that's the steady state torque, and since this thing is in this case rotating, the moment m has the effect of being a sinusoidal amplitude. It won't be a average value. So MA in this case would be whatever it is, 2400, and the mean part would be 0. So could be okay, that's only because when you have a torque, which is in this case, since it's gears, and when you are having when you have gears transmitting torques, things are pretty much rotating, right? So the torque, the things which is turning this thing round and round, is a steady part of the torque. That's why Tm is 18,000. And since it's going to keep rotating, this moment M is now going to be going positive, negative. So the top part would be in tension, compression, depending on the amplitude or which part of the shaft is moving in what direction. So let me just put the units, lbf inch and lbf. So that's the torques. Now let's see what else do we need. Okay, so we've got those. We have to compute. D is known now because we've identified the critical point. It's basically the smaller of the two diameters, the change in geometry. And then we need to get Kf and Kfs. Now to compute Kf and Kfs, we need to first compute Kt and Kts, then get Q and Qs, and then we get Kf, Kfs. So I'm going to compute the. So for this geometry, for this particular change in geometry, I need to pull up the right plot from the appendix first. That would be for Kf, Kt, and Kts. So this is something which you've done quite a few times in the past. I'm just going to pull it from one of the past lectures. It's here for the moment. This is for the torque. Okay, so what do we need? We need small r divided by small d, capital D divided by d. Let's just identify those things. So we're looking at this point, C. So R at D is 3 inch. So diameter at D is 6 inches. And then at C, I given this? Oh, there it is, 2.5. That's 2.5. Yeah, my bad. So 2.5 and 5. This is the diameter of this shaft. It's not that of the actual shaft. It's about the gear. It's the diameter of the gear. It's the radius of the gear. So it's 5 for capital D and 2.5 for small d. Here capital D is 5. Small d is 2.5, and we're given the radius. It is 3/16 of an inch. Okay, so we're all set to compute these numbers. Capital D divided by D is 5 divided by 2.5, which is 2. And R divided by D is 3/16 divided by 2.5. 0.075. Okay. Okay, now let's go and figure out the KT. That's 0.5.1. So looking here, 0.075. And then we need to go on D, capital D divided by D equals 2. This is 3, and this is 1.5. So we are somewhere in between these 2 points. Okay, so you can use any value from here to here. You can make a guess. Where could it be? Maybe it's here. No. So this is 1.8. That should be 2.0. So it's somewhere between 1.8 and 2.0. Let's just take it midway. 1.9. That's the value we'll use, because we don't have the exact value. And then let's do the same thing over here. We have 0.075, which is right here. And capital D, oh, there they have, here they've given the value for 2. So that should be this point. So this point is 1.6 midway. So this is, I just assumed it to be 1.58. So those are the values for KT on top and KTS for the one below. So KT is 1.5, KTS, sorry, 1.9. 1.5. Okay, now let's just get Q and QS. Q. QS. Okay, so that's is a function of the notch radius, and the notch radius is 3.6. Sorry, 3 divided by 16. 3/16 inch. So 3/16 of an inch is 0.1875. Is it off charts? Huh. It only goes to 0.16. So, well, the other way to do this is to use the formula. If you use the formula, that formula, and here what we can do is you can see that this line asymptotes, it basically becomes flat. So I think the assumption made here is that this line is flat, and so after this, the value is pretty much the same, and so we'll just use that value. So we'll pretty much get the notch sensitivity Q for 0.16 and assume the same value because it asymptotes to that, to being flat, right? So 0.16. We need to get SUT. SUT is 100 kpsi. This is 100 kpsi right here. And that looks like it's somewhere between 0.8 and 1. It's probably lower than 0.9. I would put it right in between 0.8 and 0.9, maybe 0.85. Just make it assume it to be 0.85. Okay, so I use the formula, which is also something I've given you. If you use the formula, you get about 0.87. So you're not very off. Okay, the formula actually gets you that exact line instead of giving you an approximate value. But 0.85, 0.87 is not too different.
Professor, I have a quick question. For the exam, if our values are like in this example is like 0.18 and which is greater than 0.16, so we can assume is equals to 0.16, right?
Yes, it's assumed because, as I said, this curve asymptotes in the sense it sort of becomes flat. So you can assume that it will remain flat like this. And so when if it is 0.18, the value will be the same.
Got it. Thank you.
Okay, so here again, we have 0.16. Now here the issue is that you can see that this line doesn't asymptote, it actually is sloping. So you probably get an error there, but if it's not given, then you're free to assume it to be the whatever is available. So 0.16 and 100 kpsi is right here. And then I need to I don't know, maybe 0.9. What I have from the formulas is actually I also have 0.9 from the formulas. So say assume it's 0.9 for QS. So Q, which came from the first figure, is 0.85. And QS, which came from the second figure, is 0.9. Okay, so let's now compute KF. 1 plus Q, AT minus 1. Q is 0.85. KT to go here. KT is 1.9. $1.765, and then KFS is 1 plus QS, KTS minus 1. 1 plus QS is, I believe, 0.9. You can check it quickly, 0.9. And KTS is 1.58. Okay. Okay, 1.522. Okay, what now remains to be done is we just need to put that in the formula, which I wrote down here. And you're done. Let me just write it down from scratch. So let's. So I think the first problem was to compute static yielding. Okay, so let's do that first. New page. The formula for static yielding is as follows. Factor of safety, which is NY, is SY divided by sigma prime max. And sigma prime max is this long formula, 16 pi t cube 4 kf ma plus mm square for the whole square plus 3 kfs a plus tm square, the square root of the whole thing. And so this will come out to be 16 divided by pi. Now we need to substitute for d, and we have two choices. D is 2.5 or 5, but since the smaller diameter has a higher stress, we use the smaller diameter. So 2.5 is the smaller of the two. For kf, forget what I wrote for kf. Kf is 1.765. Okay. Mm we know is 0. And then we know that TA is 0. Okay, so MA is 2400, the whole thing square, plus 3 KFS was 1.522. Thousand square. Okay, after putting in the numbers, we get 1.57, 10 raised to 4. And then if you use that to compute the factor of safety, SY is 80 kpsi. So the value here was in psi, and that's why I need to convert that to from kpsi to psi. Then 1.57 times 10 raised to 4. The answer is 5.09, which is quite a high factor of safety. Okay, and then let's do the second part, which is computing the factor of safety, assuming it can be a semi-elliptic. So part B. Let's start on the formula. Again, pretty long. 1 divided by n equals let's see. You quickly check this formula. This is right. SY 4k square plus 3 KFS M T M by SY square is. Okay, the two things cancel off. One is the TA part and then the MM part. By 2.5. See what KF we got. 1.765. Is 2400 divided by SE. SE is 24 tangents to 3 plus 3 KFS 1.522. PM is 18,000. SY is 80. Square here. Okay, that comes out to be, whole thing comes out to be 0.2257, but we need to put the inverse of that.